Daré lectura a la semblanza de nuestro conferencista Nobel UDLAP, otoño 2008. El Dr. Douglas Osherof nació en el año de 1945 y realizó sus estudios profesionales en la Universidad de Caltech en 1967, institución donde fue estudiante de Richard Feynman, célebre físico norteamericano y también ganador del Premio Nobel. En 1973, el Dr. Osherof obtuvo su doctorado de la Universidad de Cornell y de 1972 a 1987 formó parte del equipo de investigación de los laboratorios AT&T Bell. Durante su trayectoria como profesor, investigador y científico, el Dr. Osherof ha sido distinguido con múltiples reconocimientos, entre ellos el Memorial Simon, el Oliver E. Buckley y el premio Walter J. Gores al mérito por enseñanza. Fue seleccionado como miembro del panel de expertos convocados por la NASA en la investigación sobre la destrucción del transbordador espacial Columbia, al momento de reingresar a la atmósfera terrestre en el año 2003. El Dr. Osherof es miembro de la Sociedad Americana de Física, de la Academia de Artes y Ciencias y consejero de la Scientists and Engineers of America. En 1996 recibió, junto con los doctores David Morris Lee y Robert C. Richardson de la Universidad de Cornell, el Premio Nobel de Física por el descubrimiento de la superfluidez del helio 3 a bajas temperaturas. Este descubrimiento fue realizado en 1971, cuando el Dr. Osherof era un estudiante graduado de la Universidad de Cornell y contaba con tan solo 27 años de edad. En la actualidad, el Dr. Douglas Osherof es profesor de tiempo completo de la Universidad de Stanford en el Departamento de Física y Física Aplicada. Es un privilegio presentar y dejar en el uso de la palabra al Dr. Douglas Osherof, conferencista Nobel UDLAP, otoño 2008, quien impartirá su conferencia How Advances in Science Are Made.
No, see if you can get that working. This one works. Well, I'm pleased to see so many people here. I hope I can both entertain you and illuminate you in how science is done. This talk is a talk which grew out of a talk that I gave for the American Association of Physics Teachers many years ago, and the title of that one was The Nature of Discovery in Physics. This one is a much broader talk, and it talks a lot about how one does research, and hopefully some of you in the audience will become research scientists, and I hope that I'm giving you some good advice for your careers. Several of these, you'll see pictures. These are all my photographs. I am, in fact, I would say, a passionate amateur photographer. So this is, of course, San Francisco and the Golden Gate Bridge, and that's roughly where I'm from. I could have shown you Stanford, but I won't do that. So let's see if we do that. No, do that. This is looking bad. That doesn't work. That doesn't work. Escape. We didn't try this. No, well, it should be up and down. This is, I apologize, very strange. let's close this and open it again. Pardon me. Save. Don't save. File. Open. Now you get, that was Bali that you just looked at. Let's see, we want to go to documents. Now you get to see how completely disordered things are. My PowerPoint file. Oops, my PowerPoint files. Now we go down here. April. Today's the 26th. Open. Okay. Okay, this is a bit of the Grand Canyon in the United States, and this is the first of three subjects that I will discuss, and this one reads, those discoveries that most change the way we think about nature cannot be anticipated. How then are such discoveries made? And are there research strategies that can increase one's chances of making such a discovery? And of course, the answer to that must be yes, or I wouldn't be bringing it up at this time. So let me illuminate this with a set of linked chain of discoveries and inventions, starting with this person here. Now, this is one of my great heroes, and I suppose one of yours, even though you probably don't know who this is. Heikki Camerlionis was in a competition with Dewar. Everyone knows who Dewar is because of the Dewar flask. Back at the turn of the last century, to see who could first liquefy the lightest and most inert of the atmospheric gases. And it looked like Dewar had won around 1900 when he succeeded in liquefying hydrogen. But then, actually, in 1895, they'd already discovered evidence for helium coming from spectral lines from the sun, and within a few years, Camerlionis had obtained enough helium that he could attempt to liquefy that, which he succeeded in doing in 1908. Which is, by the way, 100 years ago to this year, and this is, of course, the centennial anniversary of that accomplishment. But then he did with helium exactly what Dewar had done with hydrogen. Dewar had pumped on the vapor above the liquid hydrogen, causing the liquid to cool, and ultimately finding that liquid hydrogen would solidify under its own vapor pressure at a temperature of 14 kelvins, 14 Celsius degrees above absolute zero. So Camerlionis tried to do the same thing with liquid helium, starting at a temperature of 4.2 Kelvin. He ultimately reached, over a 2-year period, the very low temperature of 1.04 Kelvin, but the liquid helium never solidified. Now, I personally have cooled liquid helium-3 down to a temperature of 1/10,000th of a Kelvin, 1/10,000th of a degree above absolute zero, and it remains in a fluid state very happily, even at that very low temperature. And the reason has to do with quantum mechanics, which was just being developed at the time that Camerlionis did his experiment. So after failing to solidify helium, Camerlionis didn't give up on low temperature physics. He looked around at questions of the day that he might answer with this novel refrigeration technique that he developed. And people were arguing about what would happen to the electrical conductivity in metals as they were cooled toward absolute zero. So one argument was that if the metal was very pure, that as you cooled it, the thermal energy which causes the lattice atoms to vibrate would go away, and then the conduction electrons, which are free to roam around the interior of the metal, would